Hello, all. Welcome back to our lectures. Today, we'll be talking about the physical and chemical properties of alcohol. Remember, in this module, we've started talking about alcohols, and then today we'll be specifically looking at their physical and chemical properties. Let's take it off immediately, as usual. I have a beautiful quote from Martin Luther King Jr. It says, "Love is the only force capable of transforming an enemy into a friend." Martin Luther King Jr. was a civil rights activist and a very great man, one of the greatest men that ever lived that fought for freedom, of the blessed memory. Okay, let us immediately take it off from there and get into it. Now, in this particular lesson, we have two learning objectives that we'll be addressing. Number one, we'll discuss and demonstrate the effect of hydrogen bonding, because we'll see why the physical properties of alcohols is different from those of the hydrocarbons and aromatic. That's because of this hydrogen bond. So we'll discuss and demonstrate the effect of this hydrogen bonding on the physical properties of alcohol. And number two, we're going to write equation for the reactions. The two main reactions we'll be focusing on will be the dehydration and oxidation reactions of alcohol. So these are the two main learning objectives we intend to address in this lesson, and then we'll kick it off from there immediately. Physical properties of alcohol. Now, usually remember, whenever we talk about physical properties of anything, we talk about the solubility and we talk about the boiling and melting point. So the solubility of alcohols in water depends on the number of carbon atoms they contain in their molecule. Now, remember, each of these organic class that we're talking about usually contains a hydrocarbon chain, a chain of carbons. Remember, a hydrocarbon chain or a chain of carbon and hydrogen is highly hydrophobic and is not polar. So what does that tell us? It tells us that the longer that hydrocarbon chain, the less soluble that compound is going to be, even if that compound has a functional group that is polar. So that is exactly the case of alcohols. Now, so the OH group, of course, all of them are not the OH group. The alcohol is a very polar bond. It's highly polar and is capable of hydrogen bonding with itself and water. And that is exactly why, number one, they are soluble in water and they have high boiling and melting point. So, because of this hydrogen bonding, it makes low molecular weight alcohols to be highly soluble. In fact, the low molecular weight alcohols from methanol to propanol are infinitely soluble in water because they have very short hydrocarbon chain, and because the influence of the OH group is so much that they are very soluble in water. So remember, the OH group is a highly polar bond. Let us not forget that. It's a highly polar bond. Of course, remember, if you do the electronegativity difference between oxygen is about 3.5, hydrogen is about 2.1. If you do the difference between these two, it is significant. That is giving you about what? About 1.4. So you say 5 minus 1 give you 4. 3 minus, so this is about 1.4. It is highly polar bond. And not just that, to remember. Okay, let's look at this before I move down. Now, this is a polar bond, OH group. This is also a polar bond, OH group. Remember, this is the water molecule. This is the hydrogen bonding with methanol. Methanol just have only one carbon, met. Now, this is a polar bond. And each of them, like, this is more electronegative. That is why it has delta negative. This one has delta plus. This is more electronegative. This is less electronegative. Has delta plus, the hydrogen. Now, this bond also, remember, oxygen and carbon 2 is also a polar bond, because here, remember again, oxygen is 3.5. Oxygen is 3.5. Well, let's see. 3.5. And when you subtract that from carbon, that is about 2.5. That gives you about 1.0. This is also a polar bond. You find out that, so it has two strong polar bonds. The hydrogen bond on this side and this side will make a dipole. And that is why these molecules are actually very polar. However, if the hydrocarbon chain is too long, they don't get polar. Now, the diagram I have here is the electron density map showing you the polarity of the bond. Of course, this is the oxygen. Oxygen is more electronegative. So I'm going to use a different color that you can see. So if I use, let's say green, this is delta negative, this is delta positive. If you come here to, I'm going to use blue. This one is the positive too. So these bonds are highly polar, making this, of course, these are polar covalent bond molecules. Of course, okay, let's now put that into perspectives. Large alcohols have greater hydrophobic region and are less soluble in water. Now, those hydrophobic region is too long that it will prevent them from dissolving, even when the smaller functional group forms hydrogen bond with water. Now, in 1-heptanol, water molecules surround and form hydrogen bond with the OH group. However, let's see what's happened. However, the alkyl group is too long and cannot form hydrogen bond or any polar type of polar bonds with water, making it what? Less soluble in water. Let's see what's happening. Now look at the OH group. The OH group can hydrogen bond with water here, can hydrogen bond with another water. But now look at the hydrophobic region. The hydrophobic region is too long. About 7 of them. Let's count. This is 1, 2, 3, 4, 5, 6, 7. And the OH group in carbon number 1. That's why we say it is what? 1-heptanol. Yeah, it is 1-heptanol. So 1-heptanol has, this is the hydrophobic region. So the hydrophobic region is too long. Because it is too long, this side cannot hydrogen bond with water. Therefore, overall, this particular molecule is insoluble in water, despite the fact that it can form hydrogen bond in water. So the determinant here is what? The number of carbon per molecule of any alcohol, per molecule of this alcohol or this particular molecule of alcohol decides how soluble it's going to be in water. And now let's also look at this chart. Now this chart helps us to understand what we've just been talking about. You see, this is a list of the first 7 classes from methanol, ethanol, 1-propanol, 1-butanol, 1-pentanol, 1-hexanol, 1-heptanol. Of course, these are all the primary alcohol classes. That's what I do. Because you see, the OH group is actually in carbon number 1. Now, these are their structural formulas. So the first 3 are infinitely soluble. When we say insoluble, they are infinitely in all proportion. Now, this is because this is 1 carbon, 2 carbon, 3 carbon. Now, if you get to 4 carbon and 5 carbon, the solubility begins to decrease. They become a little bit sparingly. They become a little bit sparingly soluble. Beyond the 5th carbon, the 6th carbon, they become very insoluble because the hydrocarbon chain becomes too long. So from hexanol down to other class of alcohols, other bigger alcohol chain will be very insoluble in water. So if you're going to attempt this problem, the first thing you want to look at is how big is the hydrocarbon chain? What influence will it have on the overall solubility of alcohol? Now, we now talk about the next thing, their boiling point. Of course, remember I told you the physical properties is the solubility in water and what? The boiling point. Those are the boiling and melting. Those are 2 things. So the OH group, of course, can make hydrogen bonds. You see, alcohol molecules can make hydrogen bonds with one another. So they can make hydrogen bond between alcohol molecules. Now, because they can make this hydrogen bond with the cell, remember that in the 3 intermolecular forces between the London dispersion force, the dipole-dipole, and the hydrogen bonding is the strongest. And molecules that have hydrogen bonding will always have high boiling and melting point. So the OH group can form this hydrogen bond, and as a result, alcohols have relatively high boiling point when you compare them with hydrocarbons of the same molecular weight. Remember, if you're going to make any comparison of physical properties, it has to be molecules that have comparable molecular weight. That is when you're going to begin to compare them. Because the moment they don't have similar molecular weight, dispersion begins to play a major role in that particular physical property. So now, if they're of comparable molecular weight, you find out that those molecules of alcohols will have a high melting and boiling point because they can easily hydrogen bond. A very good example is what we have here. Look at this. Now, of course, this is the hydrogen bond. Let me label it. Hydrogen bond here. This is the hydrogen bond. Remember, the hydrogen bonds are drawn with the dotted line. Now, of course, this is polar bond 2. Remember, I told you this is a polar bond 2. But you find out that now this 1 molecule of methanol. This is 1 molecule of methanol. This is another molecule of methanol. Forming hydrogen bonds with one another with what? Their polar group. So this is the positive part, this is the negative part forming this hydrogen bond. Again, this is the negative part, this is the positive forming this hydrogen bond. So the formation of this hydrogen bond results to what? The high boiling and melting point of alcohol molecules when you compare them with other hydrocarbons of similar molecular weights. And then we now get to the first reflection problem to digest what we've just said. It says, which of the following compound is the most soluble in water? Give reason for your choice. Now, if you look at this, if you can do this on your own. You can always pause this video and calculate the molecular weight of these three molecules. Now, if you look at the molecular weight of these three molecules, they are all similar. They are at least approximately close. What does that now tell you? We'll now begin to look at the functional group. Now, this is, of course, this propane is an alkane. There's no functional group here. And also, this is an alkane, no polar at all. If you look at this is an alkene. Alkenes are not polar, of course. This is propene, no polar. This is alkene. Let me put that in very well. Okay, now if you look at this, this is ether. This is an ether. Actually, this is dimethyl ether. That's what this compound is. We're going to do that immediately after this. So this dimethyl ether. Of course, this bond is polar. You see this bond now? This is partial positive. This is partial negative. This bond is polar, but it forms a dipole, not a hydrogen bond. But when you come down here, the OH group makes this molecule. Now, this is ethanol. Of course, this is alcohols. These are alcohols. The OH group here can hydrogen bond with what? With water and with itself. So here we're talking about solubility. So because of this OH group, this particular one will be the correct choice. So this is going to be the most soluble in water. Now, what is the reason? The main reason, is because it can what? It can form hydrogen bonds with water. That's the reason. It can form hydrogen bond with water molecule. So if you want to demonstrate that, okay, I can demonstrate that a little bit just to show you. I just want to put this one the way it is. Now this is our focus here. No, let me just. That's a mistake. Okay. So this is our focus here. Now, this molecule can hydrogen bond with water. Remember, here and I can form hydrogen bond. This is the negative part. Remember, this is partial negative. It's going to hydrogen bond with the what? With this side of water, which is, this is partial negative. This is, of course, partial positive. This is partial negative again. This is partial positive. So again, this side also will hydrogen bond with these to form. So this, what we have here is what? Is the hydrogen bond. And because it can hydrogen bond with water, what happens? It can make what? It can dissolve in water because it forms hydrogen bonds. So it's important you also remember that we did this data notation in the last class before this particular class, and those things will be playing an important role in all the physical properties of these compounds that are particularly polar or soluble in water. All right, we'll now go to the next reflection question. It says, draw the structure of 2-propanol. It says, use it to illustrate hydrogen bonding with water. Yes, we're going to draw the structure of 2-propanol. We use it to illustrate hydrogen bonding with water. So now you're going to draw this yourself. 2-propanol. Propanol is the longest chain. So propanol means 3 chain. So we're going to draw it. Means 3 chain. So what's that going to be? It's going to be this way. 1, 2, 3. I'm going to use shortcut. So that means the OH group is, so if you count, okay, let's label 1, 2, 3. So what it means is that the OH group is about this point. So the OH group is at this point. So you can decide to put it whichever way you want. So the OH group is at this point. So it said draw the structure of 2-propanol and use it to illustrate hydrogen bonds. So this is 2-propanol. All right. Now the second one says use it to illustrate hydrogen bonds. It says remember the hydrogen bonds are represented by what? Dotted lines. Not all the time that I will give you this, but you should remember that. So having done that, what is going to mean? I'm not going to draw water molecule around it like I did in the previous question again. So I'm going to try to give myself some space. Giving myself, I'll put it down a little bit. So I'm going to have this. And now what's going to happen? Remember, this is a polar. Here is going to interact with hydrogen. Here is going to interact with oxygen. So let me start from here. If this goes to an oxygen, in water. And then this one can go to a hydrogen. So this will go to a hydrogen. So again, remember, you can put your delta, if you do delta negative, delta positive, delta positive. This is delta positive, delta negative, delta positive, delta positive, delta negative. So this is a hydrogen bond. This again is a hydrogen bond. So you say draw the structure of 2-propan and use it to illustrate hydrogen bond with water. So when you see this kind of question, this is exactly what you expected to do exactly. All right. And make sure you don't have to do the delta notation when I ask you this, but if you're going to do it, make sure you get it correctly. Know that the one that is more electronegative, which is oxygen, gets the negative. The one that is least electronegative gets the positive, which is what? Which is the hydrogen. The hydrogen gets the positive. So this is how we do this problem. We now go to the next one. Again, a physical properties question. It says use your knowledge of intermolecular force and show how the molecule below can interact with itself. Now, remember when we said that alcohol molecule can interact with themselves. When they interact with themselves, the bond they make is hydrogen bond, and that is difficult to break. Because it's difficult to break, that will result to what? Having a high boiling point. So, it now says, do you expect this molecule to be what? Soluble in water. Give reason. Let's do. First of all, we're going to redraw it. Draw another molecule of this and use it. So, I'm going to draw the first one. So, if I have this, as the first one I have here, I'm going to use my red, usually. I'm going to use my, okay. So I'm going to draw the first one. So I'm going to draw this one here first. I'm going to draw this ring. And then I'm going to put this one here. I'm going to put it here. Now, the other one I'm going to draw, just know, I'm going to want this one to connect to the hydrogen. So I'm going to just put the hydrogen here first. And I want this one to connect to the oxygen. So I'm going to now draw it this way. You can bend it, you can turn it, it doesn't matter. So this one will make hydrogen bond with oxygen. And this is how two molecules of this can make hydrogen bond with one another. And this bonds again is the hydrogen bond. And this hydrogen bond, like I said, is what will make it to have high boiling and melting point. And again, it says, do you expect this molecule to be soluble in water? Yes. Yes, it's going to be soluble in water. And what is the reason? Because it can also hydrogen bond with water. In fact, if I'm going to draw that again, I'm going to draw the hydrogen bond it can make with water. Yeah, you can make hydrogen bond here now. Can connect with hydrogen. And here also can interact with this. So this is going to the oxygen is going to the hydrogen, hydrogen is going to the oxygen. So this is also hydrogen bond. This is hydrogen. This is a hydrogen bond. Hydrogen bond. This is also a hydrogen bond. So that is the reason why it is soluble in water, because it can make hydrogen bond with water molecule. We now go to the next thing we need to talk about, which is the second part of the objective, the reactions of alcohols. The first reaction, like I said, it was specific in the objective. We're going to look at the two reactions, the dehydration reaction and the oxidation reaction. The first one is the dehydration. So dehydration is a reaction in which water molecule is chemically removed. Water molecule can be chemically removed from a compound. It involves what we call the elimination reaction. And an elimination reaction is when two or more covalent bonds are broken and new multiple bonds are formed. So it's an elimination reaction whereby water molecule is lost. So look at me. I usually like showing my student, demonstrating in such a way that I put negative to this water. So this means removal. Let me write that well. Removal of water. That's exactly what this means. Now, this obeys the reverse of the Markov-Ninoff rule. You can say it, I usually call it, I made this up. It's not actually the reverse, but it's a kind of way I try to use it to make the student understand what I want them to do. So it obeys a kind of reverse of the Markov-Nikoff rule. Remember, the Markov-Nikoff rule is used to predict the major product of a reaction. Remember last time when we talked about elimination in alkanes, that's exactly what we did. When we talked about dehydration in alkanes, rather. So we use it to form the major hydration product. So here, we're going to be using the reverse of Markov-Nikoff to also predict the major dehydration product. We use it there for the major hydration product. Here, we are using it for the major dehydration product. So, of course, what is the rule? I usually give my students this rule. Now, you can't, remember, double bond must be formed between two carbons. A double bond is formed between two carbons. So between those two carbons, the double bond, let me use this. So the double bond is added between the two carbons that have less hydrogen. So if you count the number of hydrogen between the two carbons that has the possibility of making the double bond, the two that has the less hydrogens will be where you now add the double bond. Now, it is not always obeyed in all of them. In this one now, there's only one possibility. It's only two carbons. So the hydrogen bond must be between these two. So it's easy. What is going to happen here is that this water molecule, of course, we're going to remove OH group from here. OH plus H will give us one mole of water molecule and to form the double. So the moment you remove it, you now form a double bond. And the reason why I add this double bond, you have to use it to satisfy the carbon octet rule, or the four bonds that carbon must form, or the octet rule that carbon must form. Whichever word or vocabulary you use is actually correct. So the moment I remove this, now the moment you remove it, you find out that you now have only 1, 2, 3, 4, 1, 2 bond here, 1, 2 bond there. To make it complete, you add another bond here to form the double bond. So every dehydration reaction is forming a double bond. And what they actually form is that you convert alcohol to alcohol becomes alkene. So this is an alcohol, and when you form it, it becomes an alkene. Alkenes are known by their double bonds. Let's take some examples here to illustrate what we mean. Now, in this carbon, of course, it says complete the following and name the product. Okay, let me start by naming this one. If you want to name this one now, it has an OH group, so I'm going to give it priority, not the attachment. If you count from here, it's 1, 2, 3, 4. So 1, 2, 3, 4. So this will be an attachment, of course. So this will be where I'm going to count from because of the OH group here. So what is it going to be? So this is an attachment in carbon number 3. So this is going to be 3 methyl, and then this is in carbon number 2, 1, 2. It's the longest chain is bute, so it's going to be butanol. That's the name of this compound. Now let's see what happens here. It has only one OH group, so it's going to be only 1 mole of water that will be eliminated. Remember, this reaction is catalyzed by acid, concentrated sulfuric acid. So here it is acting as a catalyst. It is not part of the reaction. Most times students make this mistake. When I add this thing here, they want to make it as part of my reaction. No, it is a catalyst, and it is for no reason part of this reaction. Okay, if I write the catalyst well, okay, let me make sure it's clear enough. The well. So this is a catalyst. Of course, it is not part of the reaction. So what is happening? Now let's make some considerations. Now, if you remove this OH group, the double bond can form between these two carbons, between carbon 1 and 2, or carbon 2 and 3. That's the possibility. Now, what we decide? Between those two carbons, we're going to count the number of hydrogens there. So I'm going to use 2 different colors. I'm going to say, okay, how many hydrogen do I have between these two? I have 4. 1 hydrogen plus 3 hydrogen gives me 4 hydrogen atoms. 4 hydrogen atoms here. Now, it can also form between carbon 2 and 3. Let me use a different color. I'm going to use green now. If I use green and circle this, now it can form between carbon 2 and 3. How many hydrogens do I have between carbon 2 and 3? I have only 2 hydrogens here. Here, remember, I have 4 hydrogens. Here, I have 2 hydrogens. Therefore, the double bond is going to form between the bonds, carbon bonds that have less hydrogen. So it's going to form between carbon 2 and 3. So if I redraw this thing, now what am I going to have? Let me get my red back. If I'm going to redraw it, I'm going to have something like this. I'm going to have the carbon here. I'm going to have this. I'm going to have this. I'm going to have this. Then I'm going to have this. This is the carbon, the long chain I have. Of course, this is going to remain there. Nothing will happen to this attachment. Because this one has 2 hydrogen, the double bond has to be between carbon 2 and 3. So I'm going to put the double bond between this and this. So what it means is that I'm losing this OH here, and I'm losing this hydrogen. This OH and this hydrogen is what I'm losing there. Losing this hydrogen and this to form 1 mole of water. And then, of course, remember, this is this carbon here, which formerly was carbon number 1, is going to remain the same. So what is going to happen? Remember, there's still a hydrogen here. The hydrogen is going to remain. You didn't remove it, so I'm going to put it down here. And you find out that carbon has 1, 2, 3, 4 bond. 1, 2, 3, 4, everything is satisfied. So, of course, you're going to put your hydrogen at this point. So this becomes the major product. Anytime you see a problem involving the Markov-Nichols rule or the reverse Markov-Nichols rule, no need to give me the minor product, no need to give me the one that will form double bond here. It's not necessary to do that because this is the major product of this reaction. So in your exam, when I give it to you, you give me the major product, and that is exactly what you're going to be tested on. So this is how you write the dehydration reaction. So let's name it now. In naming it now is a new compound. Our priority will now rely on the double bond. Remember how we name a thing. So if you come from here, 1, 2, 3, 4, 1, 2, it's 2 in any direction. But here now, there's an attachment. To help the attachment, we're going to count it from this side. So I'm going to count 1, 2, 3, 4. So it's not going to be, the methyl group is in carbon number 2. So it's going to be 2 methyl. That's what it's going to be now. It's going to be 2 methyl. Remember before, we counted from here because we're considering this, but now we're counting from here. So it's going to be 2 methyl. Of course, anywhere you come from, the double bond is still in carbon number 2. It's going to be 2 methyl, 2 butene. That will be the name of the new compound. Remember, in exam, most times I'm not going to be testing you both the nomenclature and the reaction at the same time. But when I'm teaching, I try to make you to be versatile in thinking, to think critically, so that you'll be versatile in solving the problems when they come. All right, let us go to the next thing, the next reflection question, also involving dehydration. It says complete the dehydration reaction. Now look at what is happening here. There are 2 OH groups. That's going to tell you that we have to remove 2 moles, 2 molecules of water. 2 moles of water will go. 2 moles of H2O is going to be removed because there is what? 2 OH groups. So we're going to have 2 double bonds formed in 2 different places. What we're going to do, we're going to go back to what we need to say again. Let me start from this side. Now, remember, the chain is going to remain, but what's going to happen is where we have the OH. Look at where we have the OH group. Between these 2 carbon now, there are 3 plus 1 hydrogen, 4. Between these 2, there is 2. So the first double bond is going to form between here. So let me redraw. I'm going to use shortcut to redraw this side. I'm going to redraw it with my red. So I'm going to use shortcut for this cyclohexane. Now remember, the double bond is going to form between this and this, not between this one. So it's going to be, so there will be double bond between these 2, and there's a carbon. Remember, this OH group is gone, plus this one now. These 2 are going to be gone to form water molecules. Okay, well, let me make it together. So this is what we're losing. We're losing this to form the first 1 molecule of water. So it's gone. So what we're going to be having is, we're going to be having CH3 here, and then, oh, so no, that's a mistake. You see? Okay, that's a mistake. Let me show you what I meant there. It's good that I saw that. Let me show you. I'm going to go back to there. Now, one of the carbon loses the OH group, the other carbon loses. So you're losing 1 from here. This carbon cannot, 1 carbon can lose OH group and hydrogen. So this one loses 1 from here, and the other one is going to come from here. So please, you can correct that. I don't like the way I looked that. So this is going to be this one. It's going to be gone. Yeah. So we're losing this carbon here, loses OH, the other one loses this. So here now is 1, 2, 3, 4. Making sense. We don't need to have another hydrogen there because already carbon is satisfied here. But here, there's still a hydrogen here, like you see here, and then we put the methyl group. This is the first. So the first molecule of water will be lost to form this double bond. Now we go to this one. Now look at this one now. Between these 2, between this, there's 1 hydrogen here and this. So between here and here, we have 3 hydrogens. But between here and here, we have what? 2 hydrogens. So the double bond is going to form between this one that have 2 hydrogens. What are we going to have? So we're going to have a double bond here. Now, if we have a double bond, what it means is that we're going to lose 1. There will still be 1 hydrogen here to make it 4. This is 1, 2, 3, 4, which is correct. So we've lost this water molecule, and we're going to lose another. So we're going to be losing this one and this one here. So if you lose this one here, there's still methyl group here. So it's gone. 1, 2, 3, 4, which makes sense. Carbon is still having 4 bonds. So this is exactly the major. So this is the major product of this reaction. This is exactly what it's going to form. Again, like I said, when eliminating this, or when eliminating the OH group and hydrogen, remember, 1 carbon loses the OH group. So between the 2 carbons, one loses the OH group, the other the other loses the hydrogen. That is the rule. And of course, when you add this together, it makes a mole of water, of course. So here, we've lost 2 molecules of water to form this particular compound. And this is what? The major product of this reaction. And no need to give me the minor product, because I'm not even going to test you on that at all. Of course, let's go to the next reaction, the reaction 2. In reaction 2 here is oxidation. Oxidation, of course, we define oxidation in the review in this class that oxidation means 2 things. It means either the loss of hydrogen or removal of hydrogen, or it means the gain of oxygen. So, of course, every oxidation reaction is facilitated by oxidizing agent. The 2 main oxidizing agents here are usually the potassium dichromate and the what? Potassium permanganate. Now, both of them are usually represented as O. This O here, square bracket O, means oxidizing agent. And that is exactly what you usually see me do in most of the exams. I usually don't put these ones because you are not majors chemistry. You are just the GOB series. What I need you to, whenever I put this, just understand that it means an oxidizer. So in some reaction, particularly even in your textbook, you're going to see them written here. You can see K2Cr2O7, or you can see KMNO4 written. So that is just representing that it is an oxidizing agent. So what is happening here? Let's see what's happening here. Now, oxidation depends on the class of alcohol. But before we go, the general reaction, look at the general reaction. Look at what is happening here. If you remove this and this from this now, look at what happens. You introduce a double bond between this oxygen and carbon. It forms an aldehyde. So what happens? You form either an aldehyde or ketone. So the oxidation of alcohols forms either the aldehyde or ketone, depending on whether it is primary, secondary, or a tertiary alcohol. Remember, you have to, the most important basic thing being formed is this carbonyl carbon. So this carbonyl carbon will be formed. Now, looking at the different classes, because different classes behave in different ways. Let's see what happens here. Now, primary alcohols undergo their first oxidation step to aldehyde and further oxidation step to what? Carboxylic acid. So the complete oxidation of primary alcohols goes to carboxylic acid for complete oxidation. Remember, a primary alcohol is an alcohol that has 2 hydrogen on the carbon that has the OH group. So this is the OH group. The carbon, this carbon here has 2 hydrogens. It has 1 and 2. Or it has 1 arrow group, remember, making it a primary alcohol. So if you look at what happens here, if we remove this and this, first of all, 2 hydrogens here goes off. If you remove these 2 hydrogens, it forms what? The aldehyde. This is aldehyde group. It forms aldehyde. Now, in the second reaction, this involves removal of hydrogen. The second one involves addition. If you now take this oxygen and put at this point, remember, it can either be removal of hydrogen to be oxidation or addition of oxygen. So if you add this oxygen to this point now, it forms what? The carboxylic acid. So this is an aldehyde. Remember, this is aldehyde. This is carboxylic acid. So that's exactly what happens in primary alcohols. Now, what about the secondary alcohols? In secondary alcohols, remember, secondary alcohols have 2 arrow groups or 1 hydrogen on the same carbon that has the OH group. So look at what happens. What is happening here? You're just removing what? The 2 hydrogens. So the moment the 2 hydrogens here are removed, if you remove the 2 of them, you still have your arrow and arrow prime, and you now form the carbonyl carbon. So in secondary alcohol, the oxidation of secondary alcohol forms what? Ketone directly. They just form ketones. They form ketones. Oxidation of this alcohol forms ketones. And then what about the tertiary class? The tertiary class does not undergo a reaction. Watch this. A tertiary alcohol, of course, this is the tertiary carbon. No, the tertiary means, okay, remember, let me go back to a little bit these ones again. Remember, this is 1 primary, secondary is written this way, so tertiary is 3. So this is the primary carbon because it has arrow prime, prime. 3 arrow groups on this carbon that has the OH group, no hydrogen. So they don't undergo any reaction. They don't undergo any reaction at all. Let's take this to the next reflection question. It says, complete the following reactions. Of course, these reactions are all oxidation reactions. Let's see. Whenever you see this O means oxidation, I've shown you that it's oxidation reaction. What they're going to determine first, which class of alcohol. Now there's an OH group, so that's telling us there's a carbon here. This carbon has 2 bonds. To saturate it, this is a shortcut, there has to be 2 hydrogens. Because there are 2 hydrogens of this carbon, this is a primary, let me use a different color. This is a primary carbon, making this a primary alcohol. So primary alcohols has to go to aldehyde, and from aldehyde they go to what? Carboxylic acid. So what's going to happen? So I'm going to write it. It's in shortcut. I'm going to put this one first as a shortcut. So if I remove the first 2 hydrogens, what does it form? Remember, look at what happens here. I'm going to draw it the way it looks like. If you remove these 2 hydrogens, one from here and one from, look at what we're going to be removing this one. Oh no, a different color. If I use my green, I'm removing one from here and one from here. And if that happens, look at what I'm going to have. One will be remain. So one of them will remain. So I'm going to be having double bond to this oxygen, and then one of the hydrogen will be remaining. So this is what? This is an aldehyde. Remember the aldehyde functional group? Aldehyde. And then going further, what happens? In going further in the reaction too, if you go further, what happens? Going further in the reaction, what it means is that we're adding oxygen to this point. Now, if you do that, it's going to form carboxylic acid. Remember, we already have this one. If you now introduce hydrogen between this oxygen, between this hydrogen, if you now introduce oxygen between this carbon here and this hydrogen to form the OH group, this is what we call, this is our carboxylic acid. I'm going to give space there. This is, I use a different color. This is carboxylic acid. So this is what will happen in this reaction. All right, we now go to the second reaction. In the second reaction, let's see what's happening here. Look at this. Now, this carbon has only 1 hydrogen. That means it is what? A secondary carbon. It is a secondary carbon, or it has 2 arrow groups. There's one arrow group here, carbon, and another carbon attached to it. So what is going to happen? It's going to only have one pro. Remember, oxidation of secondary alcohols will form just the ketone. So what are we going to have? We're going to have the usual ring. This is a cyclopentane ring. And then I'm going to have a double bond here. So this becomes the product. So what we're doing is simply doing is to remove this hydrogen. Remember, you're removing this hydrogen. Now let me use a different color. We're removing this hydrogen and this one here. I thought I changed the color. Oh, sorry. So I'm removing this hydrogen and this hydrogen here. That's exactly what I removed. The moment you remove the 2 of them, you introduce a double bond between the oxygen and carbon to form this. So this becomes the product of this oxidation reaction. All right, going further, which is particularly in this reflection 7 will be our last reflection question. Now, I have a giant molecule now that has different classes of alcohol. The first thing you need to do is a complete oxidation reaction. You have to study all the places that has the OH group and see what type of carbon is it, a primary, secondary, or tertiary. Let's go. So in the first one here, there are 2, this is OH group attached here. There are 2 hydrogen already, so this is what? Primary. So it says this is the primary. We go to the next one. Here now, this is this OH group here, but it has 2 carbon attached. A carbon here, a carbon, or 1 hydrogen. If it's 1 hydrogen, it is what? A secondary carbon. And let's look at the next one. In this one now, there's no hydrogen attached at all. Or there are 2 carbons. There's 1 carbon here attached here. There's another carbon here, and there's another. It's a tertiary. So this is what? A tertiary. Remember, in tertiary alcohol, no what? In tertiary alcohol, no reaction. So we cancel, there's no reaction here. But there's going to be reaction here and reaction here. Remember, primary alcohols are going to form carboxylic acid when it is complete. Tertiary alcohols will form what? Primary alcohols will form carboxylic acid in complete oxidation. Secondary alcohols will form aldehyde. Tertiary alcohols, no reaction. So let's draw. Let's see what the product will be. So I'm going to put this one here quickly. I'm going to put my ring first. And then I'm going to go to the first one here. Remember, I'm taking away this OH group. I'm taking away this hydrogen here and another one here to form what? Aldehyde. And it reacts again to form carboxylic acid. So I'm going to make it to complete reaction. Straight to carboxylic acid. So what's going to happen here? If I take it, it's going to form aldehyde. and then the carboxylic acid. So I'm going to form what we're going to have, there's a carbon here already, we know. So this will be gone, of course. It's going to have this, and then you're going to have OH. So it's going to form carboxylic acid to straight. Remember, it's going to intermediate aldehyde and then carboxylic acid. Now, what I want you to usually do is, in exam, I'm going to give you one box. Just give me the complete reaction. That is okay. Give me, except I mention it. And in exam, I'm going to try to say, write the product of the complete oxidation of this reaction. I will always try to use that word to let you know that I don't want you to give me the intermediate of aldehyde. So it's going to form carboxylic acid at this point. Now, what about this point? I'm going to take away this hydrogen and this one just to put a double bond here. So what I'm going to have just this here to form a ketone. So let me try to label what I have, different groups. So of course, this is what? Carboxylic acid. And this is what now? This is what? A ketone. So the primary carbon or the primary alcohol gave me carboxylic acid. The secondary one gave us the ketone. So this becomes what this is exactly what the reaction will be. And then we're not done. Remember, there's still this tertiary one will remain the same, no change. Remember, it's going to remain the way it is because it does not undergo any reaction. Because this is a tertiary. Remember again, this is a tertiary one. It does not, this is tertiary and does not undergo any oxidation reaction. This is how we solve this problem. Now, to summarize this lesson, I have a reaction map. I usually tell my students, try to have a note card where you put the reaction map of each of this class of compound. That helps you to remember them. There are two main reactions we consider. Oxidation is to the right, which is O, represented by O, and dehydration. Dehydration means represented by minus water, minus H2O. This is dehydration. Remember, so dehydration will always give you alkene, one product. And remember, this obeys Markov-Nikov's rule. Markov-Nikov's rule is obeyed here. Markov-Nikov's rule. Markov-Nikov's rule is obeyed here. And then here, oxidation, depending on the class of alcohol. Now, in the oxidation, if it's a primary alcohol, it's going to form aldehyde, and further oxidation will form carboxylic acid. So carboxylic acid is the complete oxidation for primary alcohols. Now, oxidation of secondary alcohols will give you ketone, whereas oxidation of tertiary alcohols, there is no reaction at this point. So having said this about the reaction map, we've come to the end of this lecture. Thank you once again for listening. Bye at this point.